the the to be sure that those who are connected from the hall can hear clearly on the Zoom. So may I please ask those who are uh, gathered at the PTI, Petroleum Training Institute Lecture Theatre, can you confirm you can hear us? Our presenter is already on the call. So
Engineer Frank Egede, I can hear you. Can you hear me loud and clear?
Yes.
Yes, I can hear you loud and clear. So thank you very much, Dr. Adetuna, for confirming that. So it's good to know that the larger part of this gathering at the Petroleum Training Institute Lecture Theatre can hear us loud and clear. So in about 8 minutes from now, by my time is 11:02. That's about by 11:10, we should get started with the program. Thank you. And thanks to you, Adam, for being early on the call. We really appreciate, and we look forward to really very insightful session.
I at least got to be in Lagos for a few days, but I did want to get to Wari. But that's life. Can't do anything about it. So this is the second best thing. What you do need to do is make sure you take a picture of the group for me, and see if you can take a picture with me presenting online or something like that. That would be good. Yeah. Okay.
If you are ending, let me see your hand because attendance will go around now.
So again, this is Frank Egede, just to be sure everyone is on the same page. We are starting in 5 minutes. So Dr. Adetona, can you confirm everything is set over your end? Okay, so while we wait for the time to comment, let me quickly recognize some very important dignitaries here on the call. Some are section directors, past chairman of Society of Petroleum Engineers, Warri chapter, and we also have some members of the board who are also on the call. The first on the list here is Dr. Adegbite. We're happy to have you on the call. Welcome, sir.
Yeah, good morning. Thank you very much.
Yeah.
Good morning.
Thank you. So please, you can rename your phone properly so that not you, Dr. Adegbite, I'm talking to others who may not have yet renamed their device so that we can identify them and recognize them. We also have on the call, Okay Omoluwabi is also on the call. He's a member of the SP Warri Board. You're welcome to the program.
Thank you, sir.
Godson, PTI. You're welcome, and the session admin welcome you. So just for us to be on the same page, this program is going to commence in 2 minutes from now. Apologies on behalf of the distinguished lecturer. Flights were cancelled this morning, so we had to switch to this mode so that we can benefit fully from the distinguished lecture. And just to also let you know that, yes, on the call, we're about 9 participants, but I tell you that we have a hall filled with people at the PTI lecture theater. We hope that our audiovisual guys over there will be able to show us, a cross section of that all, so that we could see the turnout of people who were really anticipating and looking forward to this distinguished lecture. So they are connected, and they will also be benefiting from this program. So may I please request Dr. Adetona, who is also the program's chair, to please let us know the status in terms of working conditions over the lecture theater. If you can hear me, please, Dr. Adetona. So just to make sure that everything is... Okay, so...
Okay, it's now.
Yeah, so they reached me out directly. That they are ready, and please, can someone is okay, thank you. I think we've been able to resolve that. All right, so I've been reached out to directly that we are set to go. So thanks to the IT guys. Please, at any point in time, if it is possible, we would like to see a section of that hall, that field hall. I was there in person and I was really amazed, with the turnout for this distinguished lecture. So just before we start this lecture series, may I please confirm again from Adam, if you can hear me clearly and you can say something, let us be sure that we can also hear you.
Yes, yeah, I can hear you clearly. Thank you.
All right.
Everything
so thank
good
you
on your
very
side?
much.
Yeah.
Yeah.
Okay.
Yeah. Can hear you too.
Good.
Ladies and gentlemen, it's my profound pleasure to welcome you all to our distinguished lecture. Our lecturer is already on the call. He's he can't wait to start unleashing all that he has prepared for us, and I'm sure too that we can't wait to start asking him questions. So just before we start, I would like to follow some protocols, do a bit of some introduction, and also opening remarks as well. So, Dr. Adam, what we usually do when we have programs like this is that we have a bit of a ceremony. So don't be surprised, you'll be hearing some opening remarks from some of our directors, in particular, Engineer Eddie Oko, who is also physically on ground at the lecture theater. And immediately after his opening remark, we'll invite you to take your lecture. And before you take your lecture, we're going to introduce you properly to our audience by reading your profile, which we already have here. And at the end, we'll take a question and answer. We'll take questions and answer, and after questions and answer, and then closing remark with
oh wow,
that which will be taken by the program's chairman. We usually have a photo session, you know. Yes, we'll do some photo session, do some snapshots, you know, on the screen, so that you know, we need to archive, we need to keep this moment. We don't need to let it go. So because it's very important and dear to us. So let's set the ball rolling. May I please invite the Warri Section Director, Engineer Dr. Eddie Oko, to please give us the opening remark. Dr. Eddie, it's over to you. I hope you can hear us loud and clear.
I hope they can hear me.
Absolutely, we can.
Absolutely, we can. Okay, a very good morning to each and every one of us. I want to first and foremost welcome us for today's lecture. Adams was supposed to be here physically, but the Nigerian thing was this few minutes ago, his flight was cancelled, so that's why we couldn't make it here. So rather unfortunate, all the arrangement has been. In fact, I was even already at the airport waiting to pick him up. Adams, is really unfortunate that you are not in Warri. I can tell you for free that you have missed a lot of things. Warri, we are a small city, but very unique in so many ways. So I would have actually loved you to experience our uniqueness, so that at least that will be your take home. But be that as it may, I want to welcome us for today's DL. And today we'll be looking at something that is very insightful. I'm particularly very excited, you know, to look at carbon and how you save them, try to make the atmosphere safer for each and every one of us. I'm not the expert, I'm not the lecturer, but Adam surely do justice. I'm very inquisitive to learn, and I must gain that our making this program at the last minute the fiscal event, but at the last minute I just have to make available links to them. So you will still have a lot of industry professionals, some persons that have spent 40, 50 years in the industry that will be calling in to maybe ask questions, because I've shared the link, and they'll be listening to us, and they'll be answering questions from us. So I just do hope that we'll all sit back, relax, and enjoy ourselves, so that this 1 hour will be a very, very vital 1 hour that will be memorable in our lives as students, in our lives as professionals, and in our lives too as YP. So thank you very much, Adams, for accepting to be our dear lecturer, and we pray that everything will go well. Thank you very much. God bless you.
Thank you very much.
Thank you.
Thank you.
Yeah, so thank you, Engineer Dr. Eddie Oko, for that opening remark. Yeah, that was really very, very, very impactful, reminding us too of our uniqueness, how unique we are as a section. Yeah, so thank you very much. So we'll go straight to bringing up our distinguished lecturer for today, but before I ask him to commence his presentation, I would want to read a brief of him just because of our time. So who is J. Adam Donat? is the technical director for geomechanics and wellbore acoustics with reservoir performance division at LCLB based in Dubai, UAE. Adams joined LCLB in 1998 as a wireline field engineer, and he has held positions in Canada, USA, Norway, Malaysia, France, Romania, and the United Arab Emirates. His area of focus has been on applications of wellbore, sonic, and image data on geomechanics, geophysics, and petrophysics workflows. Adams received his bachelor degrees in geological engineering, sorry about that. He received his bachelor's degree in geological engineering from University of Waterloo in Canada. And Adam holds 7 patents in areas of borehole acoustic and aeromechanics, and is a registered professional engineer in Canada. He's an active publishing member of over 50 industry and scientific articles. Ladies and gentlemen, let us wholeheartedly welcome our distinguished lecturer for today, Adam Donald.
Thank you so much. Thank you. Again, apologies for not being present today. But so I can commence.
Yeah, sure.
Okay.
The
Very
floor is
good.
yours.
Thank you so much. So so I'm sitting in the airport right now. You'll forgive me here, but I've got lots of time before my flight. So it's a great honor to present. And this was really going to be the pinnacle of my visit to West Africa here. But anyway, at least I get a chance to present for everybody at the right time. So the talk is entitled "Insightful Geomechanical Measurements for Converting Existing Hydrocarbon Reservoirs to Carbon Storage." What I want to do first is just to acknowledge that this program, the Distinguished Lecturer Program, is primarily funded by the SPE Foundation, and it's through member donations and large contributions from offshore Europe. So definitely the Society SPE is grateful to these companies like SLB for allowing me to serve as lecturers, and there's additional support provided by AIN here. So let's begin. So when we start looking at the aspect of the aspect of, first of all, hydrocarbon reservoirs, the first thing we really concentrate on is the fundamentals of having a hydrocarbon seal and having a high porosity and permeable reservoir to produce hydrocarbons from. So we just need to make sure it's trapped. And I'm not saying it's that simple, but it's a very fundamental thing. We have to be able to construct the well, complete the well, and produce hydrocarbons in that area. When we come into carbon capture, however, if we want to use these existing reservoirs for carbon capture, there's other things that we actually need to consider that really are actually quite important. In a normal drilling environment or hydrocarbon reservoirs, we're just drilling through the overburden to get to the reservoir. So sometimes those overburden characteristics are maybe not needed as much. Maybe there's some drilling problems, etc. But generally speaking, the overburden itself is generally not studied that often. And really, it's actually very important for the CCS because it provides our reservoir seals for caprock integrity, as well as secondary and tertiary seals as well for any potential leakage paths. When we come into these reservoirs for CCS, the other thing to note is the fact that they're usually going to be depleted. So when we have these depleted zones, the stress environment is different, and we have a stress history to that depleted zone, and that's where we want to put our CO2. But the stress path and the stress characterization is extremely important here because this will really determine the economic and the safety viability of a project when we do that. Then when we come to that, maybe the hydrocarbon zone, maybe below it, in the underburden or there could be a secondary saline aquifer, could be potential. We also have lots of faults and fractures potentially as well in and around the area, which are potential leakage paths. So, you know, we have to think differently when we want to convert our existing fields to carbon storage. So this challenge here is really an engineering problem, right? It's we're trying to predict failure under the changing pressure conditions of injecting CO2. Now, what we want to do is maximize storage, maximize injectivity, and essentially production while maintaining public safety. So we want to be able to efficiently store and sequester CO2, but it has to be, A, it has to be economic, and B, it has to be safe, because this is something that we're changing here. CO2 is a gas or a material that is also corrosive and has different properties that we want to sequester and keep in the earth. Now, the main thing here, and this is really, we've heard of the frac gradient or the minimum stress. This is generally, frac gradients generally termed by drilling. This is your loss gradient. So this is your maximum mud weight before you have losses. But we need to actually understand that frac gradient in the cap rocks and in the overburden, because usually what happens is we establish a rule, an engineering safety factor of 80-90% of that frac gradient. So we need to keep that, and we need to measure that. And a lot of government, especially in the United States, Canada, Europe, require this as an engineering to pass the licenses to do the sequestration. And we have to assess the risk of this through the caprock faults and fractures, and also wellbore integrity. So, there's two things. One, we have to maintain the geological caprock, but then we need to assess the leakage also through the geology, but also the wellbore integrity. And that is actually your biggest risk in an existing field. So just to summarize, if we really break it down, we have to make sure the injection and pressure rate is not too high, because otherwise you'll break the caprock. And you need to make sure it's not too low, otherwise you break the bank. And really, that's what it comes down to, uneconomic type of projects. And this is really, a lot of the projects we're seeing in Europe now are very, very marginal in terms of their economics. So we need to make sure essentially that injection pressure and rate is optimized for this. And this is really I'll say the trick, but this is really what we need to do in carbon capture to make it work. So, by understanding this caprock integrity and overburden characteristics, what we do is we generate what we call a geomechanical model, or a 1D mechanical model. And that's a representation of rock properties and stresses at a point in time along the wellbore. So we on the right hand side here, we have we understand its structure along 3 dimensions. At the same time, we're really looking at that along the wellbore itself to look at the elastic and strength properties along with the stresses. So here, the industry standard measurements. This is, I think, the industry has come a long way. I know, for instance, the Niger Delta here, there's a lot of overpressure. So you guys know a lot about geomechanics in terms of pore pressure and drilling challenges. We use basic sonic and petrophysics logs. We need pressure data, image logs, oriented calipers. We use a lot of mini-frac with drilling losses to calibrate those stresses, as well as core data as well that we need to calibrate that in. So essentially here, what we've got is, the idea is to represent those rock properties and stresses along the wellbore, but ultimately it's a 3-dimensional problem that we're trying to solve here. So this is a 3D model used for predicting the stresses and also looking at plume migration during the injection period. So the motivation behind this talk and how I came about it was the fact that, there's a lot of discussion points with operators, and in the position I have an opportunity to talk to many different customers. And I've been really concentrating a lot of that in the Middle East, as well as in Asia, as well as my colleagues, understanding what's going on in North America as well. But the main discussion points are, well, we need this overburden characteristics to caprock integrity and seal. The problem is that, to gather that data now, we have a lot of case wellbores. So how are we going to get this information if it's so critical when we look at this? Second, we have uncertainty in the stress conditions in the reservoir because the pressure and the stresses have changed over time of that production. So we need to do a good job of characterizing that now and understanding a little bit more about how the reservoir will respond in terms of those injectivity. And last but not least, the evolution of these natural fractures. These are risks along with our wellbore integrity, but these are the factors that come into it. So essentially, the talk is broken up into 4 areas where I think there's where we see the focus on measurements and what's needed to characterize the well. So what we're looking at here is we're looking at existing well evaluation, so crystal sonic logging and well integrity. That's critical for the oilfield. Stress characterization through borehole images, sonic and MiniFrac. So I'm going to go through that. And then we'll look at fracture evaluation, use something called far field sonic imaging. And this is technology that's been around for decades, but we're seeing this as an important measurement, and we see it from all service companies actually to assess this aspect. We also, in the last part, is we'll take the core samples, impact of CO2 on rock properties. And I've got some really interesting core results as well. So through the presentation, think of your seals, think of our CO2 going into the reservoir or the host formation here, and then those potential leakage paths. So this is really the scenario that we're looking at here for CCS. So I'm going to start with a little bit of, I know I'm in a lecture hall, a virtual lecture hall, so this is some physics today, just to illustrate what we have for sonic logging. So we have a transmitter and we have a receiver. And what we end up doing is we have a transmitter creating a pressure wave on the wellbore. And in this case, it's like this is a monopole wave or a P wave. If you think of a pond, and you take a rock and you throw that rock into the pond, and you'll see the ripples going along. And as those ripples reach the side of the pond, they'll actually, those ripples will create another wave and a refractive wave along the side of essentially the pond. And that's what's happening in the wellbore. So this is the borehole here, and this is the formation. And we have fluid in that borehole. So that critical refracted wave will go along the borehole wall, and then our receivers will pick up that wave. And that critical refracted wave travels at the same formation speed as the formation of sonic. So in this case, when we look at modern day sonic, we actually have multiple receivers, and we can see these ripples. Basically, these are the P waves and shear waves and storming waves, or different arrivals along the receivers. So this is zeros time. This is in microseconds. So the movers, the slope of these lines that I'm showing. First one represents the compressional wave, which is basically like an accordion. And then we have the shear wave, which goes something like this or something like this. The slowing wave is a tube wave. And that tube wave travels along the borehole wall. It's like a tube or mud wave, basically. So that's the speed of the fluid in the borehole, essentially. So when we take this happens as we're logging up, and we have those receivers, and essentially we look at the coherence at a certain time. So that's represented here on these 3 dots. And what we do is we label these coherences every 6 inches for compression, shear, and Stallman, and then we actually project them on the log itself. So the slowest time coherence estimates the movement of the arrival events, one of the along the receiver arrays. The coherence of those signals between the slowness or the negative velocity. Now, this is for the monopole waves, and this is when we have very fast formations or faster formations where the shear wave speed is actually faster than the mud wave. Now, in the case of, I mean, you guys are probably well aware in the delta here, many were slower rocks or higher porosity sediments. And essentially, you need something called a dipole shear in this case. And these are all, this is a different wave propagation of the borehole. It's called the flexural wave. That flexural wave is like a piston, boom, that goes on either orientation of the borehole in this case. And that piston-like wave propagation for the flexural wave generates something called a dispersive wave. So the signal for that dispersive wave is changes in slowness as a function of the frequency. So this plot represents a waveform at a particular depth. And what we do is we basically look at the lower frequency part of that flexural wave, and that is our shear velocity of the formation, or shear slowness. We then project that shear velocity in the axis, and we get this plot here, which is our slowness frequency projection, and there's our shear for slowness in this case. So essentially, this is for sonic logarithm itself. This, there's a whole discipline around making sure that we provide the process rate compression and shear velocities, and this is what often acoustics or petrophysicists do. And this is really my introduction to geomechanics. I wasn't allowed to do geomechanics until I could understand sonic waves, because it's such an important input to geomechanics. Now, this is fine for open hole, but now we have a challenge here, because remember I talked about the fact that we have case hole, a lot of case hole sonic with the CCS. So what we have here is the casing itself presents a problem, because the signal, the sonic signals in the borehole has to get through the casing and through the cement to the formation. So there are two main factors that influence the quality of the casing. One is the cement quality. We need to have cement there. Bond. We don't have to have a perfect bond. We don't have to have perfect cement, but there has to be some there. And then also it's understanding the formation versus the casing slowness. So the casing itself has a slowness or a velocity as well. And in fast formations, so carbonates, low porosity sandstones, the compressional velocity is actually very similar to the compression of the formation is very similar to the compressional velocity in the casing. And it's very difficult, sometimes difficult to get that out. In slow formations, it's the opposite. It's the shear velocity of the casing is actually very similar to sometimes the shear velocity of the formation. So I don't know if there's any geophysicists in the room, but this is what we're looking at here is those technologies that we adopt from geophysical workflows to what we call filtering. And we were able to filter out the casing signals to represent some of these formation feeds. The main message here is, and this is from a paper actually at Matipec, and presented in Abu Dhabi a number of years ago, but you can see here on where my highlighter is on the well site results, without any filters whatsoever, all you see is this straight line here for the first arrival, and that's your casing. And you can see a little bit of the traces here where potentially the shear is coming in. But as we apply different types of filters or different waveform analysis from our geophysicists, basically we have the ability to filter out the formation speeds and the formation slownesses in that maneuver. My main point to this presentation is or to this slide, the takeaway is trust the fact that the industry has workflows. It's not, it is challenging in caseflow, but we can get information from caseflow logging, and all service companies have very, very good sonic tools to get those signals. And this is something that it takes some time for specialists to do, but it is, we have the ability to do it. Now, the second one is shear behind the slow formation, which is challenging as well. So here's a really good example here in the compressional projection here. So as you remember, I told you that the compressional wave is actually it's a bit easier to get in these formations because it's a definitely different wave speed than the casing itself. So you can see here, we've got basically, you can see this casing arrival is very evident here. It's a straight line, and you can see the formation slowness behind it is actually quite different. So this is easy to understand where the compression is. So now the challenge here is we've got this nice big signal. Is this really the shear? How do we see this? So remember I talked about the slowness frequency plot. So you're going to see a few of them in another few slides. But the main point is that you have some very nice big signals here. Big signal here, there's a big signal here, another big signal here. But really, the signal for the formation is a very weak signal, actually. That's actually a much higher slowness or slower than even the casing flexural in this case. And the other big signals that we have are the casing flexural waves. So this is, this is what who spend a lot of time doing in SLB as well as other service companies of analysis of this type of data. Now, for the petrophysicists in the room, what we do is there's different techniques to really QC this. And one of the things here, this is a VPVS, or the relationship between the velocity of P versus velocity of S, so that ratio. And we plot that against the compressional slowness, DTCO. Now, this is what we call a banana plot. So basically, this line represents slow formations to fast formations, and the cross plot should follow this line. And you see here, it doesn't follow it at all in certain cases. You have some data here, you have some data here. Eventually, when you QC this type of data, it should follow the right petrophysical lines. So this is with the case in flexural waves. So this is when someone made a mistake and didn't realize that what they were labeling. And this is when we have the proper formation shear, and you can see the difference between those slides where we actually follow that line appropriately. Now, so now the next scenario with cased full is the fact that sometimes you have a dual casing configuration whereby you actually have a cement on a casing, and then you may have tubing inside. So you have two things. You have annulus A and you have annulus B. Normally, annulus A, sometimes, most of the time it's liquid, but sometimes there's dual cement in there as well. The main point is that, a lot of the times it's very difficult to get annulus B because you've got a lot of signals in that casing. We're seeing what we have is we have our new technologies available whereby we actually segregate. We use two different frequencies to look at ultrasonic imaging or shallow probing, and then we look at deeper sonic response for basically annulus B into the formation speeds, as well as getting that cement evaluation. So essentially, we have our sonic frequencies here, which is 0.5 to 20 kilohertz. That's our sonic for our deeper probing. Ultrasonic is anywhere from essentially 50 to 500 kilohertz in this case. So, essentially here you've got two different types of frequencies that we're using to evaluate that. So when we look at it here for ultrasonic evaluation, these ultrasonic tools are very common, whereby we basically have our tool and we have a pulse echo. So we have something that goes out, signal goes out to the casing and bounces back. And then we have something here where we actually have like a steered beam. This is a directional type of transmitter. And what we get is we get a refracted wave here along the casing and along that cement interval. It's called the third interface echo. So there's an echo that goes into that aspect as well. So essentially, with these two measurements, we're able to look at acoustic impedance and flexural attenuation to get a map of the solids and liquids in there. Now, for the dipole sonic, or for the deeper reading sonic, we use the flexural waves again, but we have very complex signals. So you can see these lines here represent various wave modes. So think about it like it's ringing in there, right? It's the casing signal, the sonic signal is ringing in the casing. And it provides a very complex wave environments. But we actually use a lot of, this is where we use machine learning and artificial intelligence to look at pattern recognition for the casing signals going on in these complex environments. And what we end up having is we end up having a slowness versus frequency of various wave modes. And then we come up with basically a map of the bond index using our deep reading sonic. So here's an example from the cement formation evaluation. Ultrasonic evaluation, we've got annulus A inside the 13 3/8, and then we have the sonic evaluation B and C actually. So we actually have three casings in this case, but we have the azimuthal map, a flexural attenuation. You can see areas that we potentially have not as good bond in that first annulus. We have a standard bond log as well. And on the right-hand side here, we actually have a bond index here. And this is from our dipoles. But the nice part is we actually have formation speeds as well. So in this case, actually annulus A and B are cemented. So this is, and then we have annulus C as well. So we actually have three scenarios here. And what we're able to do is we're able to segregate and look at the bond within the section. So the bottom section here is dual casing or dual casing. And we were able to assess, generally it's high bond. When we get in here to the moderate bond, where we're looking at a third casing and then a lower bond index and the upper interval. My point is here is there is technologies to look at near wellbore, near casing, high frequency, that first annulus, and then we use the deeper reading flexural waves to assess that as well. Now, when we start looking at that, so then when we're done with the overburden, looking at well integrity, etc., then there's stress indicators, for instance, and measurements within the borehole itself. Now, this is important because we need to characterize the stresses. So this is our maximum, minimum horizontal stresses, so that we understand basically what's going to happen when we start injecting CO2, and we need to make sure we characterize the orientation, but the magnitude of these stresses. So I would say the first technology that has been used since really the 1980s, we have oriented calipers and we have a borehole image. This oriented caliper, think of this as looking down on the wellbore, and basically where we have a long axis. So this is our C1 axis here, and then we have an engaged axis on the other axis. This is essentially the borehole breakouts, and the maximum horizontal stress is actually in the axis of C2, and the minimum axis is the C1. Well, I even look at my pop can here when I'm squeezing. Basically, I'm bulging out on either side, and the rock is breaking on either side. So my fingers represent, in this case, the maximum stress, and it bulges on either side of the cone. Now, we can measure that with the caliper, but we can also look at an image. So this is a 360-degree image around the borehole. And then we're just unwrapping that, and that's what we see on the log. We see actually some drilling-induced fractures here. We see some borehole breakouts. So if the mud weight's too low, and we don't have enough, then we have borehole breakouts. If the mud weight's too high, then we have drilling-induced fractures. And really, that's when we can actually see failure. So remember, we have to have some sort of failure on a rock to actually image these things. Now, the interesting part is that's where the sonic also comes in. Sonic doesn't require failure; it just requires those stresses and the rock to be sensitive to the stresses from the acoustic waves. So modern day sonic also looks at something called dipole sonic anisotropy, and that's where we're looking at the fast and the safe shear wave as a function of polarization of these stresses around the wall. We then have a dual Packer configuration where we actually isolate the zones above and below an interval, and then we propagate a small hydraulic fracture in the inject fluid there. And we look at the breakdown pressure and the closure pressure of this so that we can actually measure the minimum horizontal stress magnitude and have an indication for the maximum. We'll go through that in a minute, but I'm going to take you through each of basically the dipole sonic and the microtrap with regards to the stress concentration around the well. So this is an example of a dipole sonic anisotropy log. And what I want you to concentrate right now on are the fact that we have something called energy anisotropy. So this is basically the energy in one direction versus the energy in another direction. So we use the dipole waves basically in X and Y axis. And what we do is when we pulse in one direction, we listen to see how much energy leaks into the other orientation. It's called four-component rotation. And what we're able to do is we're able to orientate the shear, the dipole spheres, based upon the energy going from one direction versus the other. And essentially what we do is when we orientate it, we come up with a fast shear azimuth. So this is the direction of the fast shear wave. And you can see actually it's very quite constant in this interval, for instance. And then after we orientate the waves, then we recompute the shear slownesses. So we end up with a fast and slow shear. And then we subtract the two, and then this is what we call our slowness anisotropy. So that's our basically low frequency shear waves or flexural waves for measuring the shear slownesses. And what I'm gonna do next is say, okay, this is the log for dipole anisotropy. How does that translate over here to our stress concentrations around the wellbore? So essentially, Remember we talked about the minimum stress where the breakout is, and then we have our maximum stress here, which is where we have our drilling and fractures. If the borehole fluid, if the pressure in it is too low, you'll have breakouts. If it's too high, you're going to have an induced fracture. So this is for the drillers in the room. This is where you're going to have losses in these drilling induced fractures, or you're going to have breakouts if the mudwork's too low, you get shear failure and get lots of cuttings. So you guys know already a lot about geomechanics. I'm just putting this into perspective. We have stress concentrations. So the stress is a high concentration here where the breakouts are, and it's a low concentration here where you have where the drilling induced fracture is. So when we put this into perspective, the acoustic waves, it's really interesting, is the fact that we have the stress concentration, induced fractures and that. But then let's put the borehole, let's put the shear waves in here and the flexure waves. So we have one flexure wave oriented at one orientation, and we have a second flexure wave oriented in the opposite orientation. So essentially, we have this stress concentration of the wellbore, and these are the high frequencies. So the high frequencies are probing near, and the low frequencies are probing deep. So on my plot over here, we see low frequencies on the left side, high frequencies over here. And what's interesting, you can see these dipole signals, these blue and the blue and the red, and you can see how they actually cross over. So what's happening is we're looking at the fast shear wave, which is represented here on the low frequency and basically on our plot. We then look at the slow wave, that's in the low frequency, and it's slower. We have a fast, then we have a slow. So what ends up happening is the stress concentration, where you're basically mapping with the high and low frequencies of our acoustic waves. So when we have this dipole dispersion plots, if we see this crossover signature, that means that we have basically, that's where we have a stress concentration with the sonic. So we can relate the stresses with the sonic. And then we have actually failure in the wellbore. So this is a case, actually, this case is from Colorado in the United States, where we have our breakouts in one orientation, and then we have our induced fractures in our fast shear azimuth in the other orientation. And that's very consistent across this interval for this log environment. So when you're looking at geomechanical data, this is a QC that you need to understand, is they need to be 90 degrees from one another, and they need to be consistent across the whole interval. This is definitely an important aspect. Now, the next one is now if we want to measure the stress, then we actually have to create a small fracture in the borehole, a microfracture. And what we do is we straddle that an interval that we want to test, and we basically seal it off two factors, and then we inject fluid. So if you look on the left-hand side here, we're injecting that fluid into the formation, and then we're breaking the formation down to create a fracture. So essentially, if we look at the pressure of the increased pressure, we'll come to a certain point where we'll break the formation. This is a function of our maximum and minimum stress and our rock strength. Okay. Once we break it, it'll actually the fluid will propagate in the fracture itself and propagate it through the process. We then can shut down the pumps. So we basically shut the flow rate down to zero. We can watch the pressure. This is a pressure transient analysis. So for the reservoir engineers or for the frac engineers, this is quite common for you guys. We watch that closure pressure, and we can reopen it again, and we can close it, and then we can shut it down again. So for a real example, this is actually something we published just last year with regards to a CCS project in the United States. We have our breakdown pressure and pressure, and then we propagate it. We let it, the first one, we just let it close. And then we have multiple cycles of injection, fall off, injection, fall off. And what we want to do is we want to look at an interval, and we keep that for that interval, we want a consistent interpretation. So if we overlay all of the pressure transient analysis, we see that we have a very consistent closure pressure and actually a representation of the minimum stress. So on this plot here, we have a lithology, we have depth. The light blue line here represents the minimum stress, okay? The dark blue shading here represents our breakdown pressure, okay? And here's our basically uncertainty of our minimum stress and our breakdown pressure all along the log interval. Now, what we do is we profile this, so we take multiple stations. So in this case, we have 2, 5, and 8 are good tests that we've done, and we use those to calibrate our minimum stress basically. Now, the one thing that you may notice is that actually in stress 5 here, this pink dot represents the breakdown pressure in that test. It's extremely high. And what we noticed actually from the wellbore image is that we actually had some dipping beds. So it's the failure of this and the failure of the breakdown of this rock is predictable through geomechanical modeling, but there's other things in here like dipping beds and other sort of rock inhomogeneities that actually can make it difficult to actually predict that accurately for the breakdown. So that's just basically some analysis of what we do for the microfrac analysis. Now, I only have one equation. This is the only equation I show for the lecture. This is one of the most important equations that geomechanicists need, which is the minimum horizontal stress, sigma H min. Okay. Now, there's a lot of letters there, a lot of Greek letters. Some of you may know them, and some people, you don't need to shy away from this. But what I want to do here is break down each one of these terms relate to the data that we acquire. So when we look at this first term, our Young modular Poisson's ratio, this is where we have our sonic data, compressional shear, as well as our core data. Okay, so our core data plays a role in this as well because we need to calibrate the sonic to the core tests that are done, because the core is a static, what we call static measurement, whereas the sonic is basically a dynamic measurement. It's basically a wave going in formation at very high frequency. So we need to calibrate that to the static property. Our vertical stress we obtain through our bulk density and integration of the density to surface. We have something called the alpha coefficients, and those are basically relating our pore pressure to stress. So basically this is obtained through core analysis. We have our pore pressure, measure of pore pressure from formation pressure tests. And then, essentially these are the E, H, and E big H terms. These are our tectonic strains. This is how we calibrate our stresses using our microfractal closure pressures. We can also use our breakdown pressures and sonic and isotropic breakouts to calibrate the max stress. So, from a practical perspective, this is what the mechanical earth model will look like for this interval. We have the various Young's modulus, Poisson's ratio, rock strength, friction angle, and then we're concentrating here on our stress profile. Okay. This is our wellbore stability plot with our calibration data and the breakdown of the minimum stress. But what we're really concentrating on is this plot here. So we have our pore pressure, and then our min and max, min-max horizontal stress are in green and red. And basically the minimum stress is calibrated by these dots. And we have our pore pressure here as well, or sorry, overburden stress here for the density. So now the key part to this is this stress profile is then translated to our reservoir model. So in this case, we have just a very nice example here, whereby we're really looking at the injection in a field. And this is a site characterization on a basin scale geological model. So essentially, this is our CO2 saturation here. And we see it's pink, so it's zero saturation, and only in this area here where we have our reservoirs, this is where we're simulating it. So we're using our initial stress profile. A 50-year simulation gives us about 143 megatons of CO2 injected. Now, what's interesting is if we update the stress profile, and only by about 300 psi, we can actually, the simulation tells us through the reservoir model, we keep everything else the same, about a 50% increase in volume of CO2 injected. My point is this is the value of having these measurements, because maybe this amount increase in volume would mean one less well for injectivity. This is really an important aspect from taking all the measurements in the geomechanics and then putting them into the reservoir model. This is exactly what we want to do. This is the important side. Now, once we've done that, and we're looking at the reservoir model, we still have to evaluate some of our potential loss zones. So it could be fractures, could be faults, but the idea here is that we have geological uncertainties. These are near vertical fracture sets, okay? We have a plan B. So what we're looking at is if I drill a borehole and I have my wellbore image, the borehole is very, very small compared to geological structure, etc. Then we look at the dipole shear. It sees a little bit more depth investigation than 1 to 2 meters, but really it's not that much. What we really want is maybe a VSP, which is, looking at 1 kilometer on the well and looking at large structure. But from evaluating this, you probably already have surface seismic, but it's a challenge too, because this is also, you want to be doing this when you're looking at maybe different structures, etc. But it's also logistically challenging as well. So what often is happening is on existing wellbores, this is where sonic imaging can help expand the size of the borehole, reduce some risk, and that can be a good way to understand if we want to invest in the VSP measurement as well. So what is sonic imaging? Well, sonic imaging is really looking at what we call the reflected signals. So on the left-hand side here, we have the borehole, we have the refracted signals. These are signals from a borehole. Those are the ones that we were using to get the compressional and shear. But really we're interested in these ones that are pinging off the side, this formation here that has those different pieces. We can also image structures that actually intersect the well. This is another way to do sonic imaging itself. And if you look on the right-hand side, this is the first published case of sonic imaging. So we have a sonic imaging on left and right of 15 meters, and this is actually a different hole scene done by a gentleman by the name of Dr. Brian Hornby. And essentially, this is a mini seismic imaging. Now, this is a 2D plot, and we've used 2D plots for a long time, but I would say that the industry has changed in recent years. So now we're able to represent sonic imaging in 3 dimensions. So what we have here, we have actually a plot in a 3D space. So this is our borehole here in yellow. And these discs represent the dip and azimuth of those reflectors, basically on either side of a fault running this way through the well. And we know that there's a fault there because we have the formation imager, but we then can extend those dips of those features and see that dip in 3D space. These are the reflection imaging of each side of the wellbore. Now, this is actually an example of a sonic imaging result from a CCS well in the United States. It was published at SPWA a few years ago, or 2 years ago. So this is an image here. We've got lots of fractures. This is actually a fractured granite. And we have the dip analysis here. We have high angle dips. We have a lot of various fractures in this case here. And basically the 3D sonic imaging, what we see is the dips that are steeply dipping along the interval, and these lines represent the distance away from the wellbore. So if we look at this in 3D space, essentially what we see is various fractures in around the vicinity of the wellbore, and you can see that's a cutout from 110 feet on either side of the well. So the idea is that what we want to do is we want to expand our borehole around so we can see deeper in the formation. We can actually see in this case fracture sets. We can see where that concentration is. This is for a vertical well. Now, here's a good case. This is the the second to last case study I've got here, whereby we have a horizontal well drilled for CCS, where we have horizontal here. This is well A. And in that well A, we see conductive and resistive fractures from our borehole images. Okay, and the strike of those fractures are north, northeast, south, southwest. We see the dipping at high dipping. So these are dipping fractures like this. Pretty much almost 80, 85 plus degrees. Now, the interesting thing is when we did the sonic imaging also, so this is in a horizontal, what we were able to do is we were able to pick up a general trend of those same fractures in the north, northeast, south, southwest direction, but we saw 2 other interesting dominant fracture sets. And those fractures were actually parallel to the well. So think about it. It's a horizontal well. We've got fractures that are actually on the side. So the borehole image isn't able to pick them up because it's parallel to the well. The sonic is able to see on either side. And this is really interesting. Now, you may say, okay, Adam, what would the operator in this case wanted to characterize the fractures? So what they did is they drilled well B, and they drilled a second well orthogonal to well A. And that was really interesting because what ended up happening is we were able, this is well A, they drilled well B, and what we were able to get is the different fracture strike or orientation from both the borehole image and the borehole, the sonic imaging data. So what we're able to do is fully characterize the fractures in 3D for this reservoir. And this is a key part, excuse me, for the fractures. Now, the last part that we have is essentially just a second. So the second part that we have here is our core testing for geomechanics. And this is really important for the integrity to measure that rock integrity of the reservoir in the seal when it's exposed to this, CO2. It impacts on, we can assess the impact on storage volume, relative perm, and then we can also look at stress magnitudes as well and under simulating what's happening in the reservoir. This is an apparatus for the core testing. You guys may look familiar, where we've got sensors around a cell that we can contain that pressure. So this is a plot that I've borrowed from and modified from my professor at Waterloo, Denise Dussault. And basically, when I illustrate here on the right top right-hand side, we've got our axial stress on the sample, and then we have our radial stress or confining stress. And what we're trying to do here is simulate the deformation of this type of sample under different stress or conditions. We're looking for measuring this delta L, which is our change in length, as well as our change in radiuses as well, under the various pressure conditions. So what we have, this is what we call our stress strain curve, and under the axial stress versus and then measuring the change in strain, our strain, radial strain is on the left, and our axial strain is on the right. So axial is this way, radial is this way. So the first part of the test, we're actually seeding the sample under the cracks, basically, and coming back to in situ conditions. And then what we're really interested in is the elastic part of the curve. So in this case, we're looking at the slope of the stress strain curve in the axial way versus the radial. And what we're able to do is come up with the Young's modulus and Poisson's ratio in this scenario. Now, when we get to the stress strain where it's maximized, that's where we get our damage and our shear plane develops. So this is a shear plane here where it failed at this point. Now, what I want to show you is an example from a limestone, whereby we've got 3 different stress strain curves for our elastic property evaluation. The blue one is pristine, so there's no CO2 exposed, it's just water, and there's basically confining stress is 2000, pore pressure 0. Then we go to the red and the green, and those represent basically our pore pressure when brine saturated, and the other ones with brine flow. And you'll see that the peak strength is lower for each subsequent test where we have more CO2. If I zoom in here on our stress strain, you can see the slope is changing for each one of the tests. So this basically indicates that we have 51% or 30% reduction in rock stiffness, reduction of 30% of strength, and we see that consistently. What we're seeing here is we're seeing the change in the rock properties due to the CO2 during these tests. Now, this is something really cool. This is the last example here. We have pre and post CT scans for the dynamic flow. And basically, this is the stress strain. This is basically the rock changing. So we have this imaging. So if you take a look on the screen, you can see the changes in the rock properties there. And you can see how the rocks are changing in the porous structure due to that CO2. Okay, so with that, I just wanted to conclude the presentation and just to illustrate here that we're 4 sections of the talk. With that, I'd like to, feedback's important. Thanks for your attention. I'm just going to take a 2-minute break before we come back with some questions, if that's okay. I'll be back in 2 minutes. Thank you.
All right. Thank you very much. That will be fine. So
yeah,
we look forward to your return in 2 minutes. All right. Again, good afternoon, everyone. So for those on the call, you can as well scan the QR code and provide the feedback for the DL. And for those who joined in the middle of the discussion, this is SP Worry, distinguished lecture, and being presented by Adams Donald. And the theme is insightful geomechanical measurement for converting existing hydrocarbon reservoirs to carbon storage. This is really insightful. We hope you already penned down some questions that you would want to ask. For those of us on the call, on Zoom, if you have questions, you can quickly signify, you raise up your hand or mute and ask your questions. While for those who are in the physical location, I've already received a list of questions from the program's chair. In case there are other questions from your end, you can kindly signify and then we'll take the questions. I mean, for those who are gathered at the lecture theater. So, okay, I can see you, Adams. You are back.
Back.
But you still need
Thank you.
some time.
Yeah, no, that's fine. Thank you. So, yeah, questions, please. Or comments.
All right. So yeah, thank you very much. This is really insightful, really, because I was following closely your presentation, and when you started with the challenges, and then providing technologies that can help us move around those challenges. Yeah, that's really made it, insightful for me, really.
Good.
Yeah,
I appreciate that.
Yeah, because talking about, data from depleted reservoir, you did mention that those data, is somehow scarce, not available, rather. And you need data to be able to build geomechanical model.
You do.
Because if you don't get the model right, perhaps you may not be able to choose your injection pressure for your CO2.
Exactly. You've summed that up perfectly. Frank.
Exactly.
Yeah, no, that's for sure.
So it's really well appreciated, and I'm sure that our participants will really be very pleased with this and getting ready to maybe ask their questions. So just because before I call on them for comments or questions, I also wanted to just mention, perhaps you may also confirm that when you talked about the technologies for geomechanical assessment.
Yes.
I was able to note down to, it appears there are 3. You talked about compressional and shear slowness in cased hole.
Yeah.
You talked about stress barrier limits. And you mentioned one additional one, which I think I'm not sure I got that correctly. Or perhaps maybe further questions from the audience can, direct you on how you could bring that out clearly for us. Yeah. So at this point, just note that down. Let me now invite comments from or questions from the participants. Like I said, while you were away, I already have a list of some questions from the program's chair, which is sent to me from those who are gathered at the lecture theater. So perhaps if there are still some questions there, and I'm not able to get them, anyone can signify over there and then ask his or her question. So, but before I read out those questions to you, are there questions or comments from those on the Zoom call who appreciate if there is any? Just to also mention, there is, I think, a 2022 distinguished lecturer who is also on the call.
All right.
I introduced him earlier, though, but I didn't mention that part. Yeah, forgive me, sir. He's Dr. Adegbite. Yeah.
Okay.
So you're back to the call again, Dr. Adegbite. Welcome. All right. So while we wait for comments, maybe I should just go ahead to read some of the comments that were sent to me by the program's chair. And please, you can as well scan the QR code on the slide, yeah, and provide a feedback. It's really very, very important. All right, so the questions, I hope you really have the time to go through all these questions, but if not, we'll email all of them to you and you'll be able to so that you can provide some responses. It borders around the techniques and methodology, from what I can see, risk management, and economic considerations, regulatory and economic considerations. So the first on the list, first on the list is, yes, you mentioned different you mentioned different measurements, geomechanical measurements that are critical when evaluating a reservoir suitability for CO2 storage. But somebody is asking, what specific geomechanical measurement is most critical? You want to take all the questions, or should I just go on, or you want to take them one by one?
I can answer them. No, that's fine. So I would say the most critical one is the microfrac, is a stress test. You need to measure the stress. Okay, that's the first thing that's the most critical, because all the modeling that we do, we're not really measuring it. That's the model. But the first one of the critical part is the microfrac. The second critical is the sonic log, because you need to have a continuous way of understanding the stress profile. So the sonic log enables that. Now, the third one, which is, I'd say all these three are somewhat mandatory, is the core data. You need core data. So you need to understand how the static properties relate to the sonic, and we need how that sonic profile, we can calibrate that back to your microfrac. So those are three key ones, really, really key ones. Now, there's other things like borehole images and calipers, etc., that measure failure. Those are used for calibration of that as well, for the maximum horizontal stress. And that's super important too, because the min-max horizontal stress, that's going to make a difference on your slippage of these fractures. So those ones I would say that those are the key measurements that we need. Everything that I put in here is for the creation of a mechanical earth model, which you need to have a mechanical earth model. If you don't have the inputs to it, then you can assume or you can model, but then that introduces more uncertainties. So I think those are the key ones that you need to have a confident mechanical earth model to plan your injection.
Thank you very much. That is really very clear. That is really very clear enough. And this question is coming also from Dr. Nelson. What role does reservoir pressure monitoring play in ensuring the stability of stored CO2?
So he's a very smart man, because that is the question that I was going to anticipate. This is the one question that comes up in every lecture that I've done. And that's the logical question. Okay, so once we have this and we start doing the injection and we have the models, then what do we look at for monitoring? This is where VSP comes in with fiber optics. Fiber optics is really being used in CO2 quite a bit, so that we can monitor the plume going. You need a monitoring wells, so you have dedicated wells in the field that are for monitoring to see when that plume actually reaches it. We have time-lapse pulse neutron logs. That's very important. We can have time-lapse seismic and or time-lapse VSP. If you have permanent fiber in some of these wells, hey, then you've got your listening source right there. You can go and you can gather multiple surveys, maybe every 6 months, every 3 months, etc., depending on your program. But the monitoring of this plume, we use seismics. We can use pulse neutron, time-lapse sonic as well, and we use fiber optics with VSPs. That's essentially what we want to do. And we can calibrate our reservoir model. As that plume gets there, we know the time, we know the saturation, and then it's a closed loop system. Does that make sense?
Yeah, very interesting. Perhaps maybe if he wants to say something, he will indicate by raising up his hand and then make further comments. But for now, I can't see any indicator. All right, so the other question has to do with economic considerations and regulatory and economic considerations. Now, how does the cost of repurposing hydrocarbon reservoir compare to developing dedicated CO2 storage sites? So this is coming from...
Yeah.
Okay.
This is another.
so
This is another expected question, and I'm glad somebody asked it. So here's the thing. I'm not going to tell you one versus the other because every field is different, but I will tell you what we've known to be the biggest pluses and minuses. So the best thing about having a depleted field or existing hydrocarbon field is you already know the history of the field. Well, I hope you do. And if you've kept records, etc., you know that. You know the petrophysical properties, you know the seal, you know how much hydrocarbon you've taken out. You know that the knowledge of the subsurface knowledge is actually quite good, generally speaking. And even if you're missing some data, you have access to it with existing well bores to be able to maybe go get some other logging. Yeah. However, your biggest risk for existing fields is your well integrity. Well integrity is by far your biggest risk. So with CCS, there's the economic side of, yes, do we have enough? Can we do that? But then the other aspect is risk. You need to assess that risk. If you're doing a saline aquifer, a brand new field, there's a lot of cost for drilling lots more wells. There's more characterization cost. However, you also then have the issue, and then you don't have the issue of the risk and the well integrity because these are brand new wells. So it's a matter of understanding your strategy and understanding the life of your the existing boreholes. In your strategy, if you have many boreholes in the field, maybe you want to truly plug and abandon some of them. Maybe some of them are injectors, some of them are producers. Injectors, some of them are monitoring. So you have to weigh the different. That's what the whole point of a project is. You have to assess that first. And what we generally recommend, doesn't matter what project you're doing, you have to do a screening process. And this is what I would recommend. First is a screening process on that aspect.
all right.
Okay.
So
Mr. Frank, you have to want to speak at the learning center. Okay, sounds good.
Okay. All right. So thank you very much. So over to those at the lecture theater, please, perhaps a comment or a question. Yeah. Thank you both for notifying me.
Frank, can we take questions from those on ground here? Because it looks like there's a kind of gap between those of us here and you guys at our hand. Yeah.
So perhaps. Can you hear me now? Can you hear me?
Yeah, I can hear you.
All right. So maybe you didn't hear me when I started. All right. So if there's any other question, somebody just another question. Sorry, I think it's echoing. Can somebody?
Sorry, I think it's echoing. Can somebody? Can you guys hear us?
Yes.
Adams,
I can hear you. I can hear you. Yeah. Just ask the question.
I can hear you. Yeah. Okay, just ask the question. Okay, let me just ask my question. Okay, my name is Dr. Eddie, and I am very interested in this topic because I have some publications relating to carbon storage. And what I want to find out is that do mechanical measurements for carbon storage, is it related to carbon sequestration or sequestration, or it's something different?
It's the same. It's carbon, carbon storage. It's carbon, sequestration or storage. Yes.
Sequestration or storage, yes. Okay, so sequestration is the same thing as geomechanical measurement for. Yeah.
Well,
okay, so
the geomechanical, the reservoir model or geomechanical model is used to assess that with the carbon sequestration or carbon storage. Yes.
Yes.
Okay, I think you're muted. I know there was a bit of an echo, but I could still hear you perfectly. So please try
yes,
again.
Please. You can respond, please.
Okay, please, do you have any questions from the audience? We want to be entertaining questions. Now, if you have any questions, please, you can signify by raising up your hand. I'll attend to you. you have any questions? Were we paying attention at all during the lectures? So do you have any?
Hello. So please, those are the lecture theater. If you can hear me, I received some questions. If there are more questions, just note them down so that somebody can ask those questions on behalf of those who are in the lecture theater.
So listen, people can, I don't mind if people email me as well. Let's see if there's a chat window.
Okay, so that's fine, Adam. Thank you very much. So do you have any response to give on the last, the question that someone asked with respect to sequestration and geomechanical modeling?
Well, yeah, there's a question here. Minimize risk of CO2 leaches through cap rock without optimizing the injection pressure. I'm not sure the question there. I don't know how to interpret that. If you could type it in again.
Yeah, same here. I'm not sure what he has in mind really. So Tres Pips, please you can retype your question. Yeah.
So how do we minimize the risk through the cap rock without optimizing injection pressure? Okay. Well, to minimize the risk of the leakage, so there's two things. Core testing is good because you can actually do core testing in the cap rock as well. Look at relative permeability of some of these shales. Believe it or not, we are doing tests like that. But the other thing is we're looking at fault seal analysis. That's another thing with geological faulting. We have faults and fractures. You can do something called a critically stressed fracture analysis. So you have your fractures from your image log and maybe your far field sonic imaging, and put them into a geomechanical model and simulate the pressure increase, see what would break, see when it would break, see at what pressure. So this is exactly what geomechanics people do. You have a model and then you make simulations. So you're assessing the leakage without actually injecting, but you do that in the model. So that's one way to do it as well. The other thing is if we already had a depleted gas reservoir, think about this: how much gas would have to go back in to pressure it up to hydrostatic pressure? So that's a volume. If your seal is good on your leakage on your borehole, in very well integrity, that's okay. Then you can increase the pressure, and then if your geomechanics is good, then you can increase it even further.
Okay. Yeah. Thank you very much for that response. Yeah.
So there. Okay. So I'll address the next one.
Okay.
Different reservoirs have geographical location have variation in temperature, and some very high, likely very low. So, okay, what's the cause of the variation? Well, this is basin modeling. Basically, you need to look at the basin modeling for different temperatures. But what I will say is if you're looking at a saline aquifer as opposed to depleted gas, the temperature of the saline fluid is very important. It's very important for the absorption of the CO2 inside the actual brine or the saline aquifer itself. So temperature is actually another thing that's very important from the reservoir engineering and the petrophysics for the CO2 absorption. Okay, so that's one thing that I will say on that. Now, so then we can another one. What's the difference between the monopole and the dipole shear? So, okay, the monopole wave is like an accordion. So my hands are like the movement. So it's like basically the wave is like an accordion coming to you like this, whereas the shear wave does this. It shears back and forth, and you have an SH and you have an SV wave. So think of the P wave like you have a pool of water and you throw a pebble in the water and you'll see it hits the water and you have all the ripples coming in. That's a P wave. That's a compressional wave. Okay, the shear wave is actually only can propagate in solids, and basically it's a shearing motion this way and a shearing motion this way, and the particle motion will actually dictate the type of mechanical property. So if you combine the compressional wave slowness and the shear wave slowness, you get your Young's modulus and your Poisson's ratio. in the waste. This is something petrophysicists to do. That's under petrophysics and acoustics, and the geophysicists do this as well. How do you calculate vertical lift? Okay, so the vertical stress, we actually take you integrate the density from whatever point in the reservoir above you. So that's your vertical, that's basically your vertical stress, is by integrating the density, the weight of the rock on top of you. So that weight of the rock will tell you what the vertical stress is. And then we're doing the measurements of the stress measurements in the borehole to get the horizontal stresses. Yes, I will. What I'll do is I'll send the copy of the slides to the organizers, and then they can distribute that in the WARI section.
That will be fine. Thank you so much. So we have
Michael,
the hands of
Michael has a question.
Yeah.
Let me say thank you, Donald. Thank you very much for being with us. It's quite unfortunate you couldn't make it to WARI.
I know.
You'll have had a little of hospitality. Yes. Again, to all that on this call, we want to also appreciate you for making it, being with us on this call. It's nice having every one of you. And I have no doubt that you have added to the body of knowledge and bringing the basic sciences into bear with the drive for the environment, carbon sequestration, to ensure that, yes, things are done in a manner that is acceptable and in a sustainable way too. Thank you once again for being on this call. I apologize for the network issues that I had. That was when the moderator invited me, and then I did not want to disturb the flow of questions and the answer session. So thank you again. I wish you all the best, especially your onward trip. Thank you.
Thank you. And I do, yes, I should probably conclude here in the next few minutes, just to make sure that I'm on my flight on the way home.
Yeah, so thank you very much. We'll conclude in just a few minutes. And thank you, Dr. Michael Adegbite. We appreciate those comments. So we still have some couple of questions bordering around research, but we'll have to email them to you. And,
give me one more question. To
okay.
To that. Yeah.
Okay. Okay. Let me just choose this one because it's about research and innovation. What gaps exist in current research on the long-term geomechanical behavior of CO2 storage reservoirs?
The fluids. So fluid interaction with the core under temperature conditions. Temperature is completely underrated right now. The other thing is if you really want to know research stuff, it's basically the wettability of, so looking at a gas versus fluid or water, of the wetting phase of inside the pore structure. There is a lot of research being done on that in the core analysis to understand the impact of if it's a partially saturated CO2 versus water, or if it's partially saturated CO2 versus oil or gas, because you're changing the wetting phase of the fluid inside the rock. We don't know if it makes a difference or not, or how big of a difference it is, but by displacing and changing the wetting phase or the rock itself may or may not make a difference. And temperature is the other one that makes a big impact as well, of not necessarily fully understanding the impact of variable temperature over time as well. The suitability of carbon storage is dependent on geological, yes, and kindly throw more light on this. Well, so the characterization is needed, right? You need to characterize it, but I think the other thing that's important is you need to characterize it as you are doing it. You need the monitoring programs to be done on that. That's the key part. You need to do your diligence on the characterization, petrophysics, geomechanics, geological understanding. That's a full field model, more than probably what you know for the existing one, plus the impact of the CO2. So if it's possible, could people in the lecture hall give a maybe I'll share I can share my screen again, but do you mind to basically do a selfie or just do an example there from and just send the picture on to maybe Frank, just so we have a picture there with my face
sure.
up there
That's going to really be the last stage of signing out of today's distinguished
Let's do that.
lecture. Yeah, definitely we're going to have a picture. So while they are getting ready, I just want to call on thanks for providing answers, comment to those questions. Really insightful presentation and full of impact. We look forward to connecting with you even after now, and also in the future. Thank you, Adam Donald. So at this point, I want
and if you could do that, and then I'm always very keen to post on LinkedIn as well. So please take a selfie, a picture there, and do what you guys can do on that. That's good. Thank you.
Okay, fine. All right. So at this point, I want to call on the program's chairman, Engineer Dr. Adetona, to kindly give the closing remarks. And after the closing remarks, please, those on the call, put on your video, and those at the lecture theater, put on the video that would show a cross-section of that of the lecture theater so that we can do a screenshot. Dr. Adetona, the floor is yours.
Want to appreciate Mr. Douglas Adams for coming and for impactful and your thoughtful lectures. I listened carefully and I thoroughly enjoyed your teachings. Your teachings discuss everything that has to do with the wellbore, to the reservoir itself, to the integrity of the reservoir, integrity of the casing, integrity of the cement, use of tools, technology, to ensure that when the CO2, I want to say thank you so much to the minds of the young students here, and I'm glad and I'm sure they are very happy to begin to pick on some of these areas you mentioned for them to start their research. And I hope as they begin to research and call upon you willing to supply them data as soon as they start their work. I want to say thank you so much. We know you came from a long distance, and also heard that the office prevented you from getting to us this morning. We've been here waiting, anticipating to receive you in our midst. But then the Murphy's Law came to play again. Well, at least we thank God for the technology, we can see your face and we can hear you. We say thank you so much. And on behalf of the SE Warrior Section 104, we want to say thank you. Thank you. And we wish you safe back to your destination. And we are sure if we call upon you next time, please kindly oblige us. Thank you so much.
Thank you.
I also want to thank
Thank you.
I want to appreciate the Section 104 for bringing this to PTI for our students to be part of this history-making event. We are so glad to be here. And we say, Section 104, may you continue to move on, and may the oil price continue to rise, so that we can continue to be happy. Thank you, and thank you. God bless you.
Goodbye, everyone. Thank you so much. Appreciate it.
Goodbye, everyone. Thank you so much. Appreciate it.
Okay.
Yeah. Thank you. Thank you.
Thank you. Thank you.
Appreciate it.
Okay.
All right. We'll be in touch. Thank you.
Right. We'll be in touch. Thank you.
The screenshots.
So I think he's out of the meeting. Perhaps he's in a very tight schedule. He gave that lecture from the airport. Probably he's about to start another. All right, thank you very much, everyone. And many thanks to SPO Richard and Tammy Biambo. Seeing you on the call. We enjoyed ourselves today. Welcome, sir.
Thank you, my director.
Yeah, so all right, for me it's bye, and let's see. Yeah, he said he would send you slides as well.
Yeah, he said slides.
Baby, let me say I don't know this. Say you okay, go. Okay, baby,
We want to appreciate each and every one of us for being here today. We especially want to appreciate.
Hello, please, section director. I would like you to take picture of the student chapter. Yeah, yeah. And your minister, I will lead your help for them, not to be left out. Thank you, sir. If you are from, come to the podium now. If you are from Fupri. You made sacrifice to be here, so sorry.
I don't know this. Say I don't need to see me again. Me a gas that you me a gas that I'm sure my body go be with I call you said this time we get sweet for party. But I'm always like something you got it something you know me something
SP Energy. Okay, so we want to appreciate each and every one of us for making our time to be here. Want to appreciate. Want to appreciate program shares And especially want to appreciate the immediate past section 104 chair, the person of engineer Dr. Eddie Woko, and we appreciate your presence in our midst today. And we also want to appreciate our faculty advisor, our own very engineer Dr. Oguye. Sorry, sir, engineer Oguye today. Want to appreciate our lecturers, want to appreciate our colleagues from Kupri, want to appreciate you all from the DTI chapter. We believe it's been an insightful session and we want each and every one of us to leverage on the knowledge that we've gained today when we want to venture into our project and our research. We believe that this lecture will play a key role in what we are going to be doing. And also want to inform that this is one of the benefits of being a member of SPE. You know, you get to network with people. If not because of some issues, we would have had our guest speaker, President of Adnan Donald, in our midst today. But because of some issues, we couldn't have him there. But thank God for technology, whereby we get to see him via Zoom. So this is one of the benefits of being a member of SPE. You get to network with people, your colleagues, and everyone. So once again, thank you guys for being here.
SPE.
Energy.
You guys, I'm supposed to be on my way to start going. Or I just feel to ship in one thing before I leave. You see, one of the gatherings you can attend in the course of pursuing your academics is in attending technical lectures and also reading journals. Adams today, it's possible you may not hear anything he has said, possibly because the communication, the sound system wasn't cooperating, or possibly he speaks different language. Possibly he was too fast, but you are here diligently, patiently waiting for him to round up, to finish. Now somebody asks you, what did you gain? Where you went to this morning, what did they talk about? I know that to get the answer will be a little bit tough. So let me try to make it very simple. You all know that it has been said that there is a desire to stop the use of fossil fuel. And the reason is because of the carbon content in the fossil. You've also heard that water may be the next source of energy. What's the difference between water and fossil fuel? Water is H2O, H. Fossil fuel, CH4, H. So if they say carbon is bad, the only thing that is not found between water and fossil fuel is carbon. And after carbon is combusted, usually it turns to carbon dioxide. Carbon dioxide is not good for the environment. It heats up the system, make the ice begin to melt, make temperature unusually high. So we say we don't want anymore. But we say we want. Do you want us to keep using fossil fuel, or we should stop it? We should stop it, or we should continue? If you want us to continue, say yeah. If you say we should discontinue, say hey. The yes have it. So in essence, we all, you had Trump. When Trump inauguration, he said, drill, baby, drill. You know what it means? He's saying, we are going back to start drilling for oil. I don't care about what you are saying about the fossil fuel environment. I need money. Go and drill, baby, drill, drill, drill. So we know in the next 4 years, before, if you survive the 4 years, the next 4 years, drilling will be taking place in the US. So if US can continue to drill, who are we to stop? Are you going to stop? How do we not make the fossil fuel better? That is why people like Donald have to look at how do we store the produced carbon. So the best place to produce, to keep it, we can find many uses for it, but one of the uses where we can keep it is to keep it back in the reservoir. And you know that for us to have a reservoir, you must have a cap rock. True of us, you must have a porous system, and the hydrocarbon there must have been depleted. So in a depleted reservoir, there are the cap rock that you have taken the oil, is saying, let's put this CO2 there. So as we are producing, we find a way to trap CO2, gather it, and pump it back into the reservoir. But the issue, all what it's saying is telling us, how do you pump it back and it will not leak out? That is the issue of integrity. Looking at how will it not leak between casing. If you have a casing hole, there's a cement behind the casing. So if the cement integrity is not good enough, then it can leak through the cement interval. Casing is suggested using a log, like sonic log, microsonic log between two cases, sonic log between one casing. Then he talk about the cap rock itself. Is the cap rock broken? Now he's talking about stress. If you look at the way that the unit of stress, what? PSI. PSI is the unit of what? Pressure. He's saying, which pressure do you use to inject this CO2? You are forcing the power for the produce inside the reservoir. You need some pressure to make it enter. And you must calculate the stress of the reservoir or the rock so that the pressure you are putting will not break down the rock. Thereby, the fluid you are injecting will not find a way to escape. That will not cause fracture. Now, you need to look at the stress in vertical direction, stress of the rock in the horizontal direction. It's also supposed to it's your rock ceiling, fraction nearby. So you need to send a lot of logs deep down to investigate if you have a nearby fault. Because there's a fault nearby, and the fault is not severe. As you are injecting from here, it's also escaping through that place. So do we get something now? So to this point, what amount of stress can break down the rock in the vertical direction? What amount of stress can break down rock in horizontal direction? How do you detect the integrity of casing and the cement? How do you find out that your cap rock is sealed, is not going to escape? You can choose any area you want to research. As you research, you must stop, get across to others. You get us his email. I'm sure he will respond to you. Thank you very much.
Now, engineer Web is not just the faculty advisor for SPE, it's also the IADC faculty advisor SPE student channel, which for now is the only student in Nigeria. Can you come up for IADC? He's also the head of petroleum engineering section. Okay. So if you have issues in your petroleum engineering area, please make sure you reach out to me. Thank you, sir. Thank you for coming. We appreciate you, sir.
Let's shine. Let's shine.
Okay, come to the end of today's program. I want to all you guys please anticipate our first general meeting. Today at time I'm really with you guys. Also, please I want to apologize for the technical issue. I believe that in our software programs, all of this will be taken care of. So please stay tuned for updates and that